Okay. So welcome at this new seminar of the Institute. Today we have a visitor from London, Professor Pierre Gélat, visiting us for 2 weeks. And today he will be talking about his research. So Professor Pierre Gélat did his undergrad studies in UK, United Kingdom, in Salford and Southampton, if I'm not mistaken, and then worked for quite a long while at the National Physical Laboratory in the UK, and now is a associate professor at University College London, specialized in biomedical innovations and also computational simulations for ultrasound. So very welcome over here, Professor Pierre Gélat, and yeah, you can start the presentation.
Thank you. So I'd like to thank, first of all, Elvin and Federico for organizing this seminar and my stay here in Chile, which is going to be for another 10 days or so. It's not just my work. This is actually a cross-faculty, cross-institutional endeavor. A lot of people have worked into this. I don't want to claim ownership for everything here by any means, and Elvin here has actually played a key role in producing this research and also in its application dissemination. So I'm going to discuss with you a Python library that was developed specifically to tackle some challenging 3D acoustic wave propagation scenarios, particularly in the context of biomedical ultrasounds, and more specifically therapeutic ultrasound. A summary of the content of the talk. I'm going to introduce you the background and context, particularly this field of therapeutic ultrasound, which you might not all be familiar with. I'm going to talk to you about the boundary element method and why it's particularly suitable to deal with a class of problems that we're interested in the context of therapeutic ultrasound treatment. I'm going to discuss an overview of the OptimUS library and provide you with some script, some top-level Python script for a specific example, which involves ultrasound propagation into the cranium for neuromodulation applications. I'm going to briefly go through some other therapeutic ultrasound applications that we've tackled and published in OptimUS. And I'm going to also look at the scenario of in utero sound propagation, sound transmission into the maternal abdomen. So here, we're not talking about ultrasound frequencies. We're talking about frequencies that you and I can hear, and the idea is to try to see what the fetus experiences in terms of transmission of external environmental noise. So I'm going to talk to you also about how we can, in some scenarios, generalize this to heterogeneous domains and nonlinearities. More on that later. And overview the strengths and limitations of our approach, and then offer you some conclusions. So I know I'm going to take questions at the end, but if you want me to clarify anything at any point, please feel free to raise your hands. I'm perfectly happy to make this as interactive a session as possible. And I'm also mindful that some of you may not be familiar with the biomedical ultrasounds and medical terminology that I'm going to broach here. I don't claim perfect familiarity myself. My background is in engineering and physical sciences, although I interact with medical scientists and doctors. So, okay. Most of you, I think probably all of you, will be familiar with ultrasound as a means of diagnostic. For example, prenatal scanning. You can look at to see what happens in an organ, provided you have a right acoustic window. How many of you are familiar with ultrasound in the context of therapeutics? Anyone? Okay. A couple. Okay. So in a nutshell, with ultrasound, it's a mechanical wave. If you propagate a mechanical wave through the body, it can actually induce a host of biophysical effects. You can basically, excite cells. You can also induce mild hyperthermia, so elevation of temperature. And in some cases, at high intensities, you can thermally ablate tissue by concentration of the acoustic energy into a point region, which I'll describe later. And also you can mechanically fractionate tissue. So there is essentially a host of pathologies that you can treat with ultrasound. And the basic principle of focused ultrasound, here you can see some focused ultrasound transducers. So these are a few centimeters in diameter. These are experimental transducers. You probably wouldn't do therapy with them, but these are the kind of things you can place in a water tank and characterize the fields, and you can do a lot of preclinical work with this. So do all of you have a background in acoustics? You do, okay. Yeah. So here you'll be familiar with this type of field. This is for a planar circular piston vibrating, rigidly vibrating in an infinite baffle, and this is in water at a frequency of 500 kilohertz. The transducer has a diameter of 20 millimeters, and it's vibrating at 0.04 meters per second. So you get this well-known pattern. You have the near-field interference pattern. You have your last axial maximum, and then eventually this decays away. So if you are to produce an acoustic lens, so this can be achieved in a variety of ways, but mainly we tend to use a concave transducer, a spherical section transducer. We use something that has the shape of a bowl. So here we've got a 64 millimeter radius of curvature, 64 millimeter outer diameter. You get this kind of pattern. So what's happening here is that you have a concentration of the acoustic pressure in this region here, and you don't have that much activity anywhere else. Now, since the physiological effects that are induced tend to be correlated with intensity, imagine squaring this and you have an even more localized effect. So this has this is actually particularly attractive if you want to focus some energy at a given point within the body without having to cut someone up effectively. So this offers the prospect of non-invasive surgery.
This is an homogeneous material.
Yes, this is an homogeneous material. That's the next part is where it gets complicated. Yeah. So it's not actually new, all this. It predates, in fact, diagnostic ultrasound, therapeutic ultrasound. The initial experiments, I think, took part in the 50s. Now it was slow development, slow uptake, but since the 2000s, we've had an increasing amount of approval by the Food and Drug Administration for these pathologies: uterine fibroids, palliative care of bone metastases, prostate cancer, essential tremor being when an individual shakes for not a specifically known reason, by contrast to Parkinson's disease, but more recently Parkinson's disease as well, and osteoma, liver tumors using a modality known as histotripsy, which is mechanical fractionation using ultrasound. That was exactly 1 year ago that this was approved by the FDA.
So all these applications involve ultrasound waves and this destructive capacity of ultrasound waves. So in the tremor, for example, essential tremor, what are they targeting, for example?
It's you're targeting a region in the hypothalamus in the brain. So in the central region of the brain, and you induce a tiny ablation. I'll show you actually a picture of that later.
Okay.
But yeah, in all these cases, we're talking ultrasound in high intensity regimes. There are therapeutic applications for lower intensities as well, which I'm also working on, which are not part of the talk, because you can induce, say, for example, mild hyperthermia, which can trigger the immune system to help fight metastases, but also you can induce what's known as cytoskeletal disruption with low intensity ultrasound and mechanotransduction effects, which can have an impact on tumor growth, hampering tumor growth. So that's the specific example, yeah, that we were talking about here. This is what a treatment looks like. You have your patient lying down. Their head is shaved because you don't want the hair getting between the ultrasound actuator and the scalp. You need to have a direct contact. You have a water cooling system in there because these transducers heat up quite a bit. And in there you have a helmet that consists of 1,024 actuators. And here they're, sorry, more or less operating in phase, and they will produce essentially a thermal ablation of a tiny region in the hypothalamus, right? And this is done under MRI guidance, but the patient is also awake while they do that, so that the focusing can be tweaked. Because they want to make sure that they'll fire a low intensity, make sure that speech and movement is not affected. And once they're happy that that's the case, then they ablate a tiny region, and it's transformative. Basically, the patient walks in shaking, they come out, they don't shake anymore, in a nutshell. So that's for the diseases for which there's approval, but there's a host of other conditions which are at various stages of clinical translation. So this can be obtained from the Focus Ultrasound Foundation website. That does quite a good job of keeping up to date with recent developments, clinical trials, etc. So okay, so that's all well. You think, well, it's already being used to treat people. So what's the issue? Well, the fact remains that as you pointed out earlier, the calculations I showed are in a homogeneous domain. What happens when you get tissue heterogeneity? What happens if you have, say, a blood vessel in the way that's through convection, which is basically taking away heat from heat deposition from where it's meant to go? You need essentially a combination of experiments and modeling to make sure that this technology is safe and effective. And a lot of that has taken place. The translation of this technology has relied heavily on a lot of experimental work and a lot of modeling work. Now, in terms of the modeling, you have a lot of challenges. You have the frequencies, the therapeutic frequencies tend to be around 1 megahertz and above, sometimes 500 kilohertz for transcranial applications. But yeah, I guess anywhere between 0.5 and 5 megahertz. So if you want to simulate the propagation of waves into the body, you have to take into account all these factors, and you have problems with the fact that your wavelengths are very small relative to the dimensions. And for this, we strongly believe that you need optimal treatment planning strategies, which will be based on high performance computing to be able to fully translate this modality and diversify to the range of applications, the diseases that I listed, but also there's some others which for which this shows promise as well. So what we want to start with here is we're going to go beyond the homogeneous domain to considering piecewise homogeneous domains. So let's say we have this domain here, which is homogeneous. We have an incident wave, reflected wave, transmitted waves. And if this is several wavelengths across, you run into, and you want to do this using a volumetric grid, solve this problem using a volumetric grid, you will have quite a few computational challenges. So you've got the issue of long computational times, dense computational grids. If there's high contrast between the external medium and the piecewise homogeneous medium, you can run into problems with some methods, and you have artifacts of numerical dispersion and dilution that can occur with, say, finite difference time domain methods and the finite element method. Also, there's been a reliance on general purpose solvers in the past, such as ANSYS and CONSOL, which may not have been tested for a bespoke application. So this diagram here, okay, so this is a box with a very fine grid. I'm not sure if you can actually see the details of the grid, but if you're looking at some figures here, you're talking if you want to do this properly, in terms of floating point operations per second, you're talking about 10 to the power 18. I'm not sure this is completely current, but essentially, if you think about this, we have a 20 by 20 box, generally speaking, that we want to deal with. Our wavelengths are between 3 and 0.3 millimeters, and a lot of the spatial discretization that needs to be used in the usual schemes will tend to require 10 to 20 points per wavelength. So that's a very big problem. So there's a range of solvers which have been used to address these challenges. Some are based on the finite difference time domain method. So these are quite easily implementable, but they do suffer from numerical dispersion and staircasing effects. And they can result in dense computational grids. Now, furthermore, the problem we're dealing with is generally a frequency domain problem, where we're switching the ultrasound on for a few seconds to induce a localized biophysical effect, but a few seconds at 1 megahertz is practically a continuous wave. So when you're using the time domain solver, it means you need to let the solution time ring long enough to capture all the multiple reflections to get rid of the initial transients, and that can be time consuming. So there's the case-based pseudospectral method, which is more efficient than finite difference time domain, but still has some staircasing and numerical dispersion issues, and also requires a finer meshing if you have high contrast media. And in some cases, like the in utero sound propagation example I'm going to give you later on, if you have air and soft tissue that's very high acoustic contrast, it wouldn't be able to, case-based pseudospectral methods tend to struggle with these kind of scenarios. We have a hybrid angular spectrum approach, which is generally a one-way propagation approach, and that's fast, but it poorly models the near fields, and you can get reasonable estimates out of it, but it's not really to be used, in my opinion, as a tool if you require accurate predictions everywhere in the field.
One question, you said nonlinear
Yes.
calculations. Do you mean like there's a nonlinear term in the equation?
In essence, yeah, thanks for pointing that out. So right now we're going to be concerned with the Helmholtz equation, but the propagation of sound inside the human body at megahertz frequencies is nonlinear. It's due to the equation of state. You have a nonlinear relationship between pressure and density. It's linear in entropy, but nonlinear in pressure and density. For that, you formulate other equations. You have the Westervelt equation and the KZK equation, which I'll touch upon later. But when I first started doing this work, there was a lot of emphasis on this, but there was also a realization that even with linear solvers, they struggled. This is why we started off with, I wouldn't say it's a simple equation, it's a misconception. The Helmholtz equation is, if you want to solve it properly, it's quite complicated. But by and large, we felt it was necessary to do this as quickly and as accurately as possible, start with and see if we could build on that to incorporate nonlinearities. So this is to say that, yes, in finite difference time domain methods, case-based pseudospectral methods and nonlinearities are more readily simulated. You just have to do a finite difference approximation of the higher not the higher order derivatives, rather the this cross terms, and well, I'll show you the equation later on, but it's reasonably amenable to that. So geometric ray tracing methods have been gaining traction. So this is as implemented in SIVA healthcare. So SIVA that's basically has been developed in France, initially for atomic energy, but to look at the non-destructive evaluation of nuclear power plants. That's how they developed the software, and now they're applying these ray tracing methods to biomedical applications. And they've had some pretty good results, but it still relies on approximations, and it's only valid over a limited frequency range. So finite element methods, the advantage you have is you're not bound by a Cartesian grid. You can resolve complex geometries and forego the staircasing effects. You can model shear waves, nonlinearities. However, you do get large memory requirements, long run times, and numerical pollution effects tend to be a given. Once you get beyond a certain Ka, you have to use higher order elements, but then you can reach a bottleneck. Although I examined a thesis last week, the week before, which delved specifically into this type of problem with interesting results. But it seems that it's only applicable to a narrow set of cases, unfortunately. I hope I'm proven wrong, because that could be a game changer. Okay, so our research goals were essentially to design a computational platform to simulate the propagation of ultrasound in the human body. Of course, we don't have to restrict it to ultrasounds. We want it to be accurate, fast, open source, traceable, and somewhat user-friendly. We wanted to basically get all the complicated work done so that people who don't necessarily have a background in mathematics, physics, engineering are able to use it. I think on that front, we've done a reasonably good job. So in terms of the applications, so this can be used for optimal designs of transducers, to look at safety guidelines for ultrasound, but also for what's known as patient-specific treatment planning, which is what they've been doing in radiotherapy for some decades now, except that whilst there were definitely computational bottlenecks even 20 years ago for radiation therapy treatment planning, the computational bottlenecks for therapeutic ultrasound are probably a few orders of magnitude higher. So who here is familiar with the boundary element method? I know these two people are. 3. Okay, right. So the boundary element method essentially solves linear partial differential equations, and to do so, you reformulate these as integral equations. So you take a volumetric problem, and if you have any number of closed surfaces in your volume, your infinite volume, then you can, if you got a suitable Green's function, which we do in acoustics, then you can reformulate your Helmholtz equation into a volumetric problem onto the surface, onto a surface rather than a volume. So this example here is not specifically related to therapeutic ultrasound, but I thought it was actually quite useful. So this is a mesh you would get with the finite element method, and this is the boundary element mesh to solve the same problem. So you know two things. First of all, you have a volumetric mesh within that domain, within that object. But also, and here you only have surface meshes. Also here, the grids are a lot coarser than in the finite element method. And so that presents significant advantages, because you can reduce the amount of degrees of freedom required to solve a problem between the finite element method and the boundary element method. So the boundary element method is also known to be highly accurate with no known numerical dispersion or pollution. And it handles unbounded domains quite easily by virtue of the Rayleigh-Sommerfeld radiation condition at infinity. In other methods, you generally have to use perfectly matched layers, which work, but they tend to work only for normal incidents, and you can run into some problems with them. On the other hand, you have very high RAM consumption, in boundary element methods, at least the methods that we've been using. I think if we were to switch to for example, the fast multipole method, you wouldn't have so many issues. But also they're very challenging to implement. It's not plug and play like finite difference time domain methods. So this shows you one of these scenarios that we're able to model in OptimUS. So what's happening here is we have an incident pressure field. Here it's a plane wave, but it can be anything you want it to be. And here you've got these penetrable objects, so which are closed manifolds. Now here you, in terms of the governing equations, you have outside of the exterior domain, the Helmholtz equation, which is satisfied. And inside each of these piecewise homogeneous domains, you have a separate Helmholtz equation, which is also satisfied. Now, in terms of the boundary conditions, you have effectively the continuity of pressure and normal velocity at the interfaces, and you have the Rayleigh-Sommerfeld radiation condition at infinity. So what we can then do is, there's I guess an infinite amount of formulations you can use. That's correct, Elvin. So here we've looked at what's known as the PMCHWT formulation because it's particularly useful with some of the problems we're dealing with. And in a nutshell, you can formulate a linear system of equations. Here, these A blocks are given by these boundary integral operators, which are given here: the double layer potential operator, single layer boundary operator, hypersingular boundary operator, and the adjoint double layer boundary operator.
Those matrices are dense, right?
Yeah, they're dense. Yeah. So which adds to the problems and the challenges. Yeah. So we get something that looks like this, and you say that's all well. The problem is that it's a large system, but what we can do is we can make this easier to solve by preconditioning it, and we've had good results with Jan surface radiation condition preconditioner, and we use H-matrix compression to reduce the computational footprint, and then that's solved iteratively using the GMRS solver. If you don't use any preconditioning, you effectively don't get good convergence at high Ka. So that was really quite transformative when our colleague Reza Hakshinaz at UCL, he was working on this, spent a lot of hours, then finally stumbled upon the right combination of a preconditioner and formulation to achieve results that meant we could actually solve some quite interesting problems. So the novel contributions here are a dedicated OSRC preconditioner, specific formulation for high contrast interfaces, and we also have effectively a test bed for different types of boundary integral operators. So an overview of the library. So we have, it's a general purpose 3D acoustic simulation platform, although we've essentially honed in on biomedical ultrasound applications. This works entirely in the frequency domain, so you don't have to deal with issues of letting your solution time ring and for long enough. You don't have to bother with the CFL criterion, and this works it within Python. You can use IPython notebook, or you can script it in Python if you want. The architecture is such that it relies on shared RAM with multi-core processing, and presently cross-platform compatibility is ensured via Docker, and we're using the BEMPP kernel, which was developed by our colleague Timo Betke at UCL. And if you want to look at our GitHub repository, it's here. So we have different source types that we can model. We can model a point source, can model a plane wave, a planar circular piston, and a bowl source like I showed you earlier, but we can also model spherical section array transducers with planar circular elements. So why do you have these? So imagine you have a bowl and you have different circular pistons attached to it. The idea is that if you vary the magnitude and phase of the voltages across these elements, you can achieve beam forming. And you can basically focus beyond obstacles and basically do some clever things with treatment planning. So I'm going to show you an example here which involves a skull slab. But so this is the kind of input we require. You have a surface mesh of triangular elements, and there are P1 elements that we use. So this is for a skull slab. This is for some ribs, and we require G-mesh format as inputs. And generally speaking, 3 to 6 grid points per wavelength tend to be sufficient to solve the problems that we want to solve. So about 3 years ago or so, we were invited to Elvin and I to participate in this international software benchmarking exercise. This came to a realization that there were a lot of open source and commercial software simulating the propagation of ultrasound inside the body being used globally, but there was never really any proper validation carried out. I mean, we've been very big on this to validate against analytical solutions and other solvers as well, but not everyone within the community was, saw the how can I say, the need to do this. A lot of the people using these methods were experimental scientists, biologists who just wanted something they could, play with, and they didn't necessarily care about validation. But for the first time, there was this coordinated effort to introduce benchmark scenarios and get everyone to produce results on these benchmarks and to provide answers. And so we published this in JASA a couple of years ago. So this shows you one of the benchmark cases. We have an acoustic volt transducer here going into the cranium, and you can see the focal region around here. And another reason why this exercise was prompted is because transcranial neuromodulation was gaining traction, and you had a lot of people experimenting on themselves, putting transducers at the back of their head. Yeah.
What frequencies are you modeling here?
So for transcranial,
Yeah, for the benchmarking that you were.
it was 500 kilohertz.
500
Yeah,
kilohertz?
yeah. That's generally the accepted frequency for transcranial ultrasound, between 200 and 1 megahertz, but generally 500 kilohertz.
And that translates to what wavelengths? Because you mentioned the number of elements per wavelength, and
Okay.
I'm thinking it's quite small, right?
Yeah, it is. So C upon F, so 1,500 divided, it's 1 millimeter wavelength. So yeah, if you want lambda upon 4, it's 0.375 millimeters. I think 0.375 millimeters for the elements edge length. Yeah. So this iTrust consortium was really basically put together to try and create some standardization for these in vivo in human applications. So here's a list of the participants. Phase 1, it was basically looking at a numerical comparison using ideal sources and ideal geometry. So this was led by Professor Brad Treby at UCL. And what I'm going to show you here is some of just very briefly, the type script that we can use to solve the propagation through this skull slab. And you can see it's fairly straightforward. So we import OptimUS. Okay, here we have the time and date. Here we define our source, the bowl source, in terms of the frequency, radius of curvature, the location, so basically where it's situated in the Cartesian grid, the velocity, and the number of point sources per wavelength, which we put at 23. This is slight overkill, but it does actually provide better agreement in the near field. So, and here we create our bowl source. Then what we do is, okay, this is incident fields parallelization parameter. There's different options, so we choose the multi-processing one. Here we define our exterior and interior domain properties. So we have water outside and we have bone for the cranium, cortical bone for the cranium, sorry. Create the geometries by importing the grid, the mesh file, and we scale the geometry because that's in millimeters. We want that to be in meters, and then we create our model, and then we solve it. So that takes just over 3 minutes to solve. And here, this is for the post-processing stage. We specify a grid. We specify some other parameters to do with the H matrix assembly. And then this is the real part, and this is the magnitude of the fields. So your transducer is somewhere around here. And you can see here relative to the plot I showed you earlier, this is the same transducer. You can see there's an aberration of the beam that's introduced by the cranium. And this highlights why it's actually important to do some treatment planning. If you want to target a region in the brain for neuromodulation applications, so this is prospectively to treat mental health conditions such as depression, then you want to know where your ultrasound is going. This shows you that your beam, your hotspot is not necessarily where you want it to be. So on a workstation, this takes about 7 minutes to solve. Now it's a lot quicker. Our workstation is 7 years old. Recently, I was in France, and our colleagues there have basically much improved processors, and it was incredible. I mean, a job that took 2 days to run on our workstation ran in about a couple of hours. So that was really quite transformative. I'm pleased to say I'm going to be getting one of those workstations soon myself. So we have other applications. This is for kidney. You can target kidney tumors using ultrasound. And this is what a multi-element array looks like. You can see here, all these little dots are elements. So here you're focusing on the kidney.
It's like the spherical.
Yeah, so it's a spherical section, but you can see it better here. There's a spherical section, but also you have 256 elements. And you can, here they're all vibrating in unison, but you can introduce different phases and magnitudes to each element to produce beamforming effects.
When you say element, you mean like something that is produced?
Piezoelectric elements, yeah, sorry, yeah. So there are little piezoelectric transducers, 3 millimeters in radius each. And this is for osteomus. So this treats the upper right side of the tibia. And this is another multi-element array, but it's oh gosh, I can't see it so well here, unfortunately. Yeah, so that's it's got a slightly different geometry. Right, I'm mindful of the time. So in utero sound transmission, I told you about this earlier. That okay, so in this day and age, well, I'll say for at least 100 years, since the Industrial Revolution. We've been exposed to unprecedented levels of noise. And we all know that this can have a psychological impact on individuals, but also there's evidence of physiological impact during pregnancy. So this can be occupational noise at work, for example. Even in an MRI scanner, an MRI is actually quite loud, or leisure noise such as at the gym, fireworks, loud music. Now, we know that from mid-gestation, the fetus can respond to sound stimulus. And there's a host of adverse effects reported in the literature. Now, this includes, premature birth, reduced birth weight, preeclampsia, gestational hypertension. Now, the thing is, all these studies rely on all these adverse effects that have been characterized following epidemiological studies on large cohorts. So we don't really know how this comes about. It could be due to stress, higher cortisol levels that are induced due to stress, which have physiological adverse effects. So what What we think, however, is that we wonder whether in fact, part of the explanation is sound being a mechanical wave that, contrary to what we may perceive, that the maternal abdomen doesn't really shelter the fetus much from external noise. So to do this, we worked with some colleagues at University College Hospital and King's College in London to get some MRI scans of pregnant women. We modeled key anatomical groups, and we used OptimUS to predict the average pressure inside the uterus. So this is at frequencies between 20 and 20 kilohertz, so the human audio range. So I'm going to show you very quickly some convergence tests on nested spheres. So that's at 10 kilohertz. So you can see this is the analytical solution. This is the OptimUS solution. So we have very good agreements. And 20 kilohertz, we also have very good agreements. So that's quite reassuring to look at. And we have about 4 to 5 elements per wavelength which are sufficient to basically give results accurate to within 10%. Now, we tried to solve this with finite element methods, and it wasn't possible. We ran into numerical evolution errors, and we could not get these kind of scenarios, the analytical solutions to be, couldn't get the FEM to be in agreement with the analytical solutions.
This was what setting, sorry, what experiment specifically?
Oh, sorry, you talk about here?
Was this what you tried with finite elements and it didn't work?
Yeah. If you can get it to work, yeah.
What boundary condition were you using outside?
Oh, I think we tried a range. We tried initially FEM-BEM coupling that just wouldn't converge. We tried, I think, a Robin condition. Do you remember what Ganesh used in the end? He tried a number of things, but essentially, what happened is that you get it to work at low Ka. As soon as you were getting higher up in the frequencies that we wanted to look at, then it would just break down. And we were using fourth order elements, I believe. So it might be worth revisiting. I don't know, but I think if you want to do it with FEM, it will have to be time domain, because the other issue you have is also actually, it's a good point. Maybe no, it's actually FEM-BEM that poses the problem with iterative solve. Yeah, I mean, we did have a good crack at this, and we came to the conclusion that BEM was just far easier. So we got some. This is what comes out of an MRI scan. So we smoothed it. So that's the abdominal region. That's the uterus. Amongst some of the other anatomical groups. We have different meshes depending on the frequency range we're considering. And this is one of the scenarios. And up here you can see, okay, so we have a plane wave traveling, and you have this interference pattern due to the reflections, but you have quite significant transmission into the uterus here. This is in decibels. So on 3 data sets, we did some frequency response calculations, and you can see that basically up to about 1 kilohertz, most of the stuff gets through. You have even resonances that occur simply because of modal behavior inside the different cavities induced by the objects you're describing. So that we've built upon these results, and we actually just submitted to Nature Communications yesterday. A big milestone. We'll probably get rejected, but we thought we have to try anyway. Okay, I'm just very quickly nonlinearities and heterogeneities. So this is the Westerveld equation I was telling you about earlier. So in certain cases, if we assume harmonic excitation, and we make the assumption of weak nonlinearity, we can end up with these sets of equations. These are Helmholtz equations with the right-hand side for each harmonic induced by the sound field. And here we basically solve in nested boxes. And this is the field for each harmonic, and this is a comparison with a known open source package, and you can see we got good agreements. This, yeah.
You're solving so you're basically solving the nonlinearities with this boundary
Yeah.
element.
Yeah, so if we make this assumption of weak nonlinearity, you get these separate Helmholtz equations with the right hand side. Now the thing is, we want to generalize this to right now we don't have any, we're not incorporating any density variations. We're assuming density variations between boundaries is negligible, but this is something that we really want to try and work on. So heterogeneous domains. So this is the work by one of Elvin's students, Danilo. Essentially, we're assuming in the exterior domain that we have something homogeneous, but inside an object, a penetrable object, we're assuming that we have spatial variations of sound and density. And there's some initial tests that were carried out on a sphere, which worked well, nice convergence. And this is for a heterogeneous cube with a spatial variation of density. Right now, I mean, so I think he's just going to try doing this with a heterogeneous skull slab. So I'm going to be very curious to see how this pans out. There's good convergence, but I think it can lead to large problems because we need about 10 grid points per wavelength to get reasonably accurate results. But there's also some work in progress using H matrix compression to try and address this. So that's all work in progress. So yeah, I need to conclude really, don't I? Strengths and limitations. So we can solve problems with high contrast media, no volumetric grids. We make it also quite easy for the end user. We don't have domain truncation effects, fewer elements per wavelength than with other solvers typically. And I think this is a big selling point, is that we don't have any known numerical pollution and dispersion effects, which are an inevitability with other solvers, and also no staircasing effects associated with Cartesian grids, voxelized grids. We do need a large amount of RAM, and currently the model we have relies on shared RAM, and this imposes a computational bottleneck on large problems. We've managed to run problems on 1.5 terabyte nodes, but beyond that, they're challenging to come across, and so we probably need to look into strategies to mitigate this. And we're toyed with basically heterogeneous, piecewise heterogeneous domains and with nonlinearities, but there's still some more work to be done. So, okay, I think that probably concludes what I have to say. So thanks for your attention, and I'm happy to take some questions.
Any questions from the audience? Yeah, Federico.
I have questions regarding the medical part. Sure. So when you put these waves, does it feel like a massage, or are you actually like? Is it more like a massage, or is it more like you're actually breaking chemical bonds inside? Because whenever I see like something being focused on the brain, I get a little bit nervous, right?
Yeah, of course. But still, you gotta understand that didn't happen from one day to the next. There was. It took a long time to get this to be approved, both in the US and in the UK. So yeah, you are denaturing protein. That's what's happening. You are in that mode. You're denaturing protein.
You're what?
Denaturing. So you're cooking tissue, really, like frying a steak. Really. Except you're doing it in a very localized region, and typically the focus is about the size of a grain of rice.
But still concerned in the sense that we're talking there's a lot of differences patient to patient between the the tissue density, right, and the bone geometry
Mhm.
of the skull, right, where the wave has to go through. So that's gonna change completely how you focus and
So
does the patient, you said the patient was awake?
Yeah.
They can move a little bit, move?
No, they can't, they don't move, their head's in a vice.
Okay.
It's clamped, they can't move. Okay, so I understand your concerns. The other option is a craniotomy. So you break the cranium open and you carry out surgery. And that is much more invasive and much more prone to adverse long-term effects. Mobility effects, I don't know if you've had if you've had people who've undergone brain surgery for tumors, for example, they don't come out unscathed most of the time. So it's not to say, I mean, this specific essential tremor scenario is one of the ideal ones because it's really at the center of the brain. Peripheral regions of the brain are much more difficult to locate, to get to using these ultrasound transducers. At the center of the brain, it's usually quite okay.
Still, I insist on something, and it's the differences in bone density and bone geometry of patients.
Yeah.
So this is what I was going at. I'm guessing there's a lot of patient-specific studies that are made before, right?
Yeah, so the thing is, you're right that some people may not be candidates for this because their skull is too dense. It happens. And if the skull is too dense, you can't get enough ultrasound inside to create the thermal damage required. So in terms of taking into account the heterogeneity of the skull, that's challenging because what comes out of your MRI scan or CT scan is of resolution generally of 1 millimeter of voxels. You need to mesh at sub-millimeter levels to correctly predict what's happening. And so you may be actually by doing so introducing more uncertainties and assuming homogeneity. This is work in progress. It was going to be one of the next phases of this iTrust planning exercise, but I think it was time is of the essence. Really, we were fortunate in that it was a pandemic. A lot of us didn't. It's not that we didn't have much to do. We had, but there was kind of like we could rally behind this common cause and justify the time that we put in to solve this, and it was a really nice exercise. But to replicate this within the 15 or so different groups, it will be challenging again. So there's a question at the back.
Yeah,
Yeah.
so,
Go for it.
so the bones typically have this very special structure where it's very dense outside and inside it's very spongy.
That's right, yeah, cortical and cancellous bone, yeah.
Yeah, so my question is whether in this experiment it makes sense to homogenize that or to separate the outer layer from the.
So it's been done actually in France. The group that's been working with SIVA, software that geometric ray tracing software I outlined earlier. This is effectively what they did. They looked at a heterogeneous skull and they built an equivalent region of cortical and cancellous bone that would give the same results. But there's one actually further issue here. It's the fact that we're treating bone as an acoustic medium. Now, strictly speaking, it's viscoelastic, and if you want to characterize its properties, that's also challenging as well. So this is why in terms of treatment planning, again, this transcranial scenario made it because you don't require anything that sophisticated. I think they do a bit of geometric ray tracing, but between that and the feedback from the patient, they've had a very good success rate. But yeah, I mean, of course, this is all stuff we'd like to try and take into account, but there's still a lot of unknowns in terms of the input parameters of the models.
Is the whole library running on Python, or there is some Fortran C++ code?
Yeah, there's some C++ code in there as well. There's some Python code, but the number crunching is in C++.
For the boundary element method, sometimes, what I hear, integrating, you have to take into account similarities, right?
Yeah.
And so you have to be a little careful with the integration.
Yeah.
You
That's all taken into account, yeah.
And it's accurate and everything's working.
So we've done extensive checks against, solutions on spheres, nested spheres at high Ka. The only issue we have, and this is what's expected, it's close to the boundaries. Now, in singularity issues, if you're careful with what you're doing there, in terms of calculating the pressures on your grid nodes, you're generally fine. It's really, when you're calculating field locations, we increase the integration order, the quadrature order if we want results close to the boundary, but that can cause problems as well. So we have some tweaks there, but it's just, I think, one of those known artifacts of boundary methods. But yeah, with dealing with the known singularity problems, that's well taken care of.
You find the question, yeah, Sebastian?
Seems to me that with OptimUS, you have a very large data set of cases. Is anyone trying to operate on learning or something like that?
Is anyone trying to what?
To operate on learning or beams or something like that? Incorporating machine learning.
Oh, yeah, okay, so we had discussed this. I mean, I think it's probably actually a topic for discussion this week or next, how we can do this. We had thought about certain ideas, but mainly to identify suitable preconditioners. Are you talking about physics-informed neural networks in particular? Is this what you're?
I'm talking really about rate of learning, since you can, for example, you fix the skull model, say something.
Yeah.
And then you can change the parameters, for example, for the density that seems to worry Federico.
Okay.
And just doing a lot of data sets, changing the parameters of the operator, like the operator is the same, but you change those parameters. And then you train a network to predict.
Okay, so that's interesting, and I guess it's probably something to look at. And I think in this day and age, if you want to get research funding, you have to incorporate machine learning components. So
What about adaptive methods? Or is implemented in the library?
the what?
Adaptive methods.
Adaptive methods. So more specifically, would you?
For example, when you have a boundary element method solution and you calculate the error by element and you mark the element which contributes with the higher error contribution. So you refine the mesh in the.
Oh, I see. Okay, no, yeah. So we've used adaptive mesh. Well, we've had to do it to solve very large problems. In essence, if you refine the grid close to where the field is located, you coarsen the grid elsewhere, then you actually get some pretty reasonable results where you're surprised. Could get away with 2 elements per wavelength in some parts of the grid for large domains. Yeah. Yeah.
Well, I would like to know, I haven't seen the OptimUS yet, but is it possible to get the radio frequency, I mean the reflection that gives the transducer in the simulation or just? Oh, okay.
Yeah. So basically the scattered field that comes out directly out of the solution. Yeah. And that can be useful for a host of applications. It means you can separate the incident and scattered field, which you wouldn't be able to do so easily in other methods. Actually, you could kind of do it, but you'd have to the scattered fields comes out of your solution directly.
Yeah, and you show the image, so which beamforming methods used to?
Yeah. Okay. So in the past, what I've used is there's different methods you can use. If you have an obstacle in the way, let's say, okay, I've got this cylinder here, I've got my source here. The naive method is to switch off the elements that are in the path. And that's what people have done clinically. There's another method which is known as time reversal acoustics, where you take a point source here, and then you propagate the point source up to the surface, and then you average your pressure over the elements. You flip your phases round, then you propagate forward, and then you effectively have an optimized focusing vector to avoid the cylinder. So that works. I mean, all these things, they would work best if you had an infinite amount of elements, and that, you know, if you could have a sphere that encompasses your object. What I've worked on in the past is constrained optimization, which I found worked best. It's actually the subject of my thesis quite some years ago, but yeah. Yeah.
Thank you.
Thank you very much, Pierre, for this
Thank you.
interesting talk. We will be around for another week, so if you would like to talk, just send a message.